Okay, I successfully unmuted.
Yeah, wonderful.
Uh, so thank you, everyone. Uh, and I guess I want to make the same pitch that Walter made in the beginning. That of course, seeing some people's faces does immensely improves my life. So if you're willing to keep your video on, that would be lovely. Um, so I'm going to tell you about actually something where the connection to the title of this semester or workshop is more in the open question than in actually what we can answer. It should be an application of uh, reinforcement learning, but instead what we're going to do is applying classical kind of learning. And maybe the question is, can we do something better if the players might use fancier format of learning? So I want to talk about learning as it might be used by players in a game, and it's joint work with Jason Gaitonda, who is my student at Cornell. Um, so, oops, something's not so good here. So I guess repeated game, you think of something like packet routing. Every iteration, there are new packets and you want to send them, and maybe the games that I have previously worked on, though that's not the game we're going to consider now, uh, it's congestion that's causing the problem, and things slow down as their congestion. As you might know, there is at this point a growing and I think beautiful literature that learning is a good way to think of what players might be doing in a game, or at least is a interesting solution concept with uh, reasonable theorems. So I guess the assumptions are that agents play a fixed game over and over again, which could be routing or actions. They selfishly try to maximize their own utility or cost, minimize the cost, and that they're using some sort of learning. And the most known notion that's getting used here is that they use some form of no regret learning. And then the idea is that initially they don't know what to do, but later on they do. And you all know what the no regret condition is. They do at least as well as a single condition with hindsight. I like this behavior assumption, uh, despite that the open question I'm going to end with is that maybe reinforcement learning is offering us should offer us better assumptions here. Um, I guess I want the properties I want is oh sorry that there are many algorithms of this sort, so they're easy algorithms that can be implemented. It sounds like a decent behavior assumption. All I'm asking the agents is, hey, there is a really good solution. Please notice it, or at least do at least as well. If something much better that was also easy to see, then, well, how come you didn't see it? And then I guess compared to other notions, it's less restrictive, and uh, uh, there's some evidence that it might be true in practice in some settings. Um, there are nice theorems. I guess classically, maybe at this point, 20 years ago, we had all these theorems about the price of anarchy in games. And almost all of them, all but very few exceptions, they extend to the same theorems about quality of outcomes, assuming the weaker assumption that people do, every player employs a form of no regret learning. So this was a super fast 1 minute history of where I'm coming from. And now comes the main point I want to make. All this work makes an assumption that unfortunately I would view as certainly not reasonable, possibly as bad as silly. And here is the assumption that really bothers me is that we are assuming that every iteration the players play a completely new copy of the game. No carryover effect, no effect between runs, beyond the fact that they learned something on how to play from the previous run. So we're asking, oh, again, I have problems with this. Is this a reasonable assumption? And just to get you started on how good the assumption is or how bad the assumption is, if you're talking about morning rush hour, then I think this is reasonable. No matter how bad Monday traffic was, by Tuesday morning, the cars are gone. But it's not reasonable on the second by second or millisecond by millisecond internet traffic, if a packet's not getting through, then either it's still sitting there trying to get through, or it got dropped and we're going to resend it. In any event, any unsuccessful packet is bothering you in the next iteration, continues to bother you in the next iteration. And this is where I'm thinking that and that's sort of to foreshadow what I won't be able to do and what is maybe the open problem here, is that in the version of car routing or morning rush hour traffic, no regret learning seems like the right assumption. And maybe in the second by second packet traffic, it's not. Your action has a direct effect on the future. Namely, if you didn't get your packet through, it's going to be in your hand and you're going to have to send it through later. And this is true for the other guys also. So that's what I'm trying to study. What can we say in a competitive game when players are used some form of learning? And I'm going to study it not in the very realistic assumption of packet routing on the internet, but in a super simplified model of packet routing not in the internet. So let me tell you what is the model that we're studying. I'm happy to ask, actually, anyone feel free to ask questions in the middle, especially clarifying questions. So here is the model that we are looking at. It's an infinitely running system. It's queues that are getting packets, and they want to send them to a server. And it's going to be that these queues each are using their own machine learning to figure out which server is any good and where are the other guys going, sending their packets. So, you know, I want to go someplace where the service is pretty good and there's not so much competition. So every queue will have some sort of arrival rate, a Bernoulli process at rate lambda I for arrival rate, and every server has a service rate, probability mu j that the service arrives. Every iteration, each queue gets to send one of its packets to one of the servers, their choice, and they're going to try to learn which one. If the server will choose one of these packets to serve, and if it doesn't succeed serving the packet, either because it failed or because there was too many packets sent that way, then it's going to send it back. So literally, this is what I wanted to model, the leftover effect. If your packet doesn't get served, then I guess it's going to have to get served later. It's sent back to you, and you can try it again in the next iteration. And again, as I said, every queue will use a no-regret learning algorithm to figure out what to do. So this is the model. What I'm going to ask is the very reasonable algorithmic question: how much bigger server capacity do I have to guarantee to make sure that this system will be stable and that we're not going to have an infinite backup of queues? So I'm going to compare how much capacity do I need if they're selfish compared to how much capacity do I need when they were not selfish. They just, you know, coordinated on who should send that. To get everyone on the same page, again, two maybe things that should take 1 second each. Two super simple examples. Example one is one queue, one server. So that's what it looks like. And I assume I don't have to spend even a second on this. Obviously, what you need is that the arrival rate should be strictly less than the service rate. And then the queues will stay bounded. You can think of this either as a very simple queues and server question, or as a biased random walk with bias towards the 0 point. And I guess we also know that if mu equals lambda, then they actually back up, and mu bigger than lambda, lambda bigger than mu, then it backs up linearly, obviously. The second super simple case, and it's still almost as super simple, is one queue and many servers. So this is in part to remind you that I made the assumption that you can only send one packet at a time. So this queue really needs to figure out which server is the good one and then try to send there. So this is really a multi-arm bandit problem. These servers are the arms, and the queue, there's no competition, just wants to figure out which one is the best server and try to send it there. And I guess what we need is that the lambda should be less than the biggest mu. And in fact, this model was studied in a NIPS 2016 paper by Krishnaswamy, Sen, Johari, and Sakotai, where they actually did a much more thorough analysis of how the packet length, packet backup will actually go up for a while the queue is trying to figure out what's going on and then go back down. So a very detailed analysis of what happens to queue length. What we're going to do is a competitive version. So there are multiple queues, multiple servers. They're going to be non-cooperative and selfish. And I guess I'm going to want to measure, again, remember the question was, how much capacity do I need on the servers to have this non-cooperative selfish thing work out for them? Before I can do that, or I can even tell you what might be the right answers or questions here, I should give you the baseline. So what's the baseline? The baseline would be, suppose I coordinate. How much capacity do I need if I were to coordinate? So maybe you won't be surprised. The answer, it's very natural. If I sort the queues and the servers in the natural order, that is better servers first and higher arrival rate of queues first, then this is the condition. For every K, the top K server should have strictly bigger capacity than top K queues. This is super not surprising. Remember, again, everyone can send to one server at a time. So the top K queues can only use the top K servers even if we tell them how to coordinate on it. And if there's not enough capacity on those, they're in trouble. And indeed, this is the condition. So hopefully this sounds believable to everyone. So now comes the real question. Okay, I don't coordinate. I want to have them compete. How much server capacity do I need then? And I admit I swept a detail under the rug, which I have to fish out from under the rug before I can talk to you guys, is if there are multiple packets arriving to a single server, which packet will the server choose? And I guess I want to propose that there are two natural answers to this question. One is uniformly random, one of them, and the other one that the packets come timestamps and I do oldest first. So I either give priority by age or I don't do that, and then it seems like uniform random is maybe the most reasonable. So here is the results that I'm going to want to give you a little hint of, or little ideas of how we prove of. So step number one, uniformly random is really bad. That is, with n queues, I might need as much as a factor of n times more server capacity to get anywhere. If the selection is uniformly random, then unless you have insanely more server capacity, selfishness really, really kills you. And this one, I will basically convince you with an example in about a minute. And then on the more constructive or positive side, if you do all this first, all you need is a factor of 2. That is, if you have twice as much server capacity as what would have been needed had they coordinated, then as long as they all are reasonable learners, by which I mean they satisfy the no regret condition, then they're going to not back up. Again, the factor of 2 is sharp here. That is, less than a factor of 2 won't do it. So let me give you a sense of what kind of proof, so how does this work? So first of all, the uniform selection example, I think, is a little insightful in thinking about how this works out. So here is my uniform selection example. I can make this C something polynomial in n, but actually to keep it simple, think of C as a large constant, like 100, or your choice of a very large constant. This system has this C slack in the capacity. That is, if I were to coordinate, or I have to tell them that, look, guys, every one of your queues has its matching server. It has a service rate factor of C above what your arrival rate is. Please use it. And then we're all set. Everything is coordinated. But maybe it's also tempting to believe that you will know that, well, actually, that's not what's going to happen. And what's wrong here, and what might happen instead, is that many of the queues will say that, my assigned queue server is really bad. It basically has a, 1 in n kind of service rate. if I only go higher up, I would get, it's random selection. If 7 of us go up, we get a 1 in 7 service rate. Isn't that a lot better? And a whole bunch of them, some polynomial depending on n, we'll choose to go up, and that will be the Nash equilibrium here. We'll do it in learning. There is no, if you satisfy the no regret condition, they will all switch up, or many of them will switch up. And what's wrong with switching up is that the big Q cannot clear. Like the service rate for this top Q here, actually I'm pointing probably to the wrong side. The top Q, I'm not doing well with the pointers. Top Q here has too high service rate and it won't be able to get across. So I guess I'm claiming that this doesn't happen if you have timestamps. And in fact, a factor of 2 is enough. Here, instead of giving you any hint of the example that shows that the factor of 2 is tight, which interestingly is actually pretty similar to the previous example, I'm going to want to give you, or use my minutes here to give you a sense of how the proof goes. So here is a rough idea of the proof. It's a potential function proof. What I would like to say is, actually, let's start from, this is an infinite system. If I want to claim that it will stay stable, I have to realize that in the infinite time horizon, all kinds of horrible things will happen. So what I have to basically prove that when the system is in a bad state, it will actually keep getting better, it recovers. So I need a measure of what's a bad state, and then I need an argument that when that state is bad, life tends to get better. And that's basically what's happening. That is done by a potential function. The intuitive definition of the potential function is what I wrote here. That is, phi tau is the number of packets that are h tau or older, and the potential function is sum of all the phi taus. So every packet that has a particular h tau contributes tau to this potential function. So this is really the sum of all the ages of the packets. That's what this potential function is. But I prefer to think about it that way because I want to argue about the phi taus, that is the number of tau or older packets, separately. The main tool we're going to use is a nice probability theorem of Pimentel and Rosenthal, which says that a random process, if it's sufficiently regular and has negative drift whenever phi is large, then it remains bounded in expectation. So what we're going to prove that the expected value of phi, that is the sum of the ages of all the packets, will stay bounded because, as I try to prove to you in a sec, it's sufficiently regular and has a negative drift. I didn't even define sufficiently regular, so definitely next slide we'll focus on the negative drift, and then I admit to you what sufficiently regular is, which is a more technical part. So what I want to say is that if you satisfy the no regret assumption and you have a factor of 2 slack in the capacities, then will imply negative drifts whenever this phi is big. That's sort of the main theorem I want to prove. And instead of going through the sort of details of the proof, I want to give you an idea of why the proof is true. I hope to the level that most of you will say that, yeah, I guess that's believable or sounds reasonable. So I want to focus on a particular age, say tau, and want to look at all the tau-old packets or all the Qs that have tau-old packets, and want to know for a long enough window and want to say, okay, what are these guys doing? And I want to say there are 2 cases. Case number 1, as indicated by this picture, or suggest to indicate by the picture, that these tau-old Qs during this window spend a lot of packets towards the best servers. Remember, they had priority. So whenever they sent something, one of them got served because tau or older, they all have priority. So probably a lot of them got served, and therefore this tau phi, that is the packets that have tau or older, decreased in number because they got served. I have to worry about the second case, which would say, actually, this servers didn't send it to these good servers. They somehow apparently did something else because maybe their learning algorithm messed up, or I don't know why. And then I guess I want to claim no regret will kick in. I want to say, oh, you guys are not sending, none of you are sending to the good servers, but you have priority. Had you sent to the servers, you would have had priority. Why didn't you send it to the servers? So that must mean, if you satisfy the no regret condition, that you're getting at least as much service as you would have gotten at these servers. And that's all I needed. It's either you got served, but case one, or if you didn't use this to get served, you must have been getting served someplace else because of the no regret condition. And then what I need to do is, of course, do this all scales simultaneously and add it up for every tau and imply the negative fit. To be honest, I did sweep a technical detail under the rug, or a couple of technical details. One I almost admitted, and then I swept it under the rug. To make this work, I actually, instead of wanting no regret in expectation, I probably want it in high probability. Certainly that's how we can make it work. And instead of wanting it over all the whole horizon, I definitely want it over every large enough window. As I pointed out, this is an infinite system. Bad situations will arise. Many different bad situations will arise. So different queues will have backed up, and I want them to have the no regret condition. Whenever it got really bad, the next window, you satisfy the no regret condition. So again, the main message is, because it's an infinite system, super unlikely bad things will happen. And I want you to have a condition that helps you recover whenever that happens. And indeed, if you have no regret with high probability over every sufficiently long window, that's a good enough condition for this. The second thing is that I was actually cheating with the potential function. And instead, I'm using a deferred decision version of the potential function. Tau IT here is, or TIT here is the age of the ice queue, the oldest packet in the ice queue at time t. And this expression that's on the screen instead of phi tau is an estimate of how many tau packets will there be at that point, given the age of the oldest packet. And that's our actual potential function, not the number of packets. The reason I'm doing this is because sufficiently regular in actually proper mathematics was that it had to have bounded moments. And this estimate on the number of packets has bounded moments, whereas my original one does not actually. So it's a technical distinction, but I think the main idea was the use of the no regret condition. So let me actually end with a bit of discussion on what I promised in the beginning of what might be closest connection to the reinforcement learning or other form of more long-term learning. So I like learning in games. I still like it. I have worked on it now for a while, but I think these carryover effects are an important feature that our community has been mainly or completely ignoring it. And I think it's nice to get back to it. And I think it's a natural, no regret is not the matching condition here in this carryover effect because of the direct effect of your actions have. I could imagine working on other problems where carryover effects actually apply. And many of you might know that this sort of killer application here is adductions, where the carryover effect is called your money. If you win in an auction, you have less money. If you lost, you have more money, which is maybe a bigger killer app than this queuing. But maybe I want to end with this. In an upcoming work, we actually have a result saying something that even more strongly says that no regret is the wrong form of learning. What does no regret do? No regret evaluates whether you like to send to a server by the instantaneous success you have at the server. Wrong measure. But you should be evaluating, if I were to send to the server for a long time, how successful will I be on the long time? That is not the same measure as the instantaneous success. And in fact, if the learners or the queues are patient enough to look at the long-term success rate as the thing they're optimizing, then it turns out this E over E minus 1, which is only 1.58 something, is enough for extra capacity. So more patient behavior does actually needs less extra capacity. You can ask me, why didn't I give this talk instead? And I admit there are two reasons. We're in the process of writing it up, and hopefully will get posted very shortly. But second, because I don't actually have a learning result here. This is a Nash equilibrium result, in part because I don't know what the definition of learning I want to use. So that's where the open problem comes in. The matching version of learning here should be something that you don't evaluate what you like step by step, you evaluate it over periods as you somehow figure out how you change your strategies. And I think many of you in the audience, if not every single one besides me, is better experts in all the possible notion of learning. I hope you can give me good advice of what definition of learning might match this sort of longer term patience by the queues. And thank you so much.
Thanks a lot, Eva. Do we have any direct question to Eva? And then we're going to open the floor to just more general questions to the three speakers.
I have a question. Just a technical question. I may have missed this in the beginning of the talk. What's the model of arrival of packets to the queues? When you say they receive packets at a certain rate, what does that mean?
Bernoulli independent rate lambda I for QI.
So there's no adversarial aspect to this.
No, and I guess that's a good question. You may be thinking that this use of Pimentel-Rosenthal theorem, at least to me, came from the adversarial queuing theory paper. And we did wonder whether the same results we're doing here would work in an adversarial model. I suspect it would, but I guess the paper that we have works out the random model, doesn't work out the adversarial version.
Thanks.
So Eva, when you had one queue, you made the connection to the multi-arm bandit. And then you moved to multiple queues, which naturally would connect to multiplayer multi-arm bandit, but you didn't make that connection. Is there a reason?
So possibly it's my ignorance of what's known as multiplayer, multiple bandits. I guess I know a more of that form of where the players are coordinating.
Right. Yeah.
And I'm not aware of my players are competing.
Yeah. So I don't. So we have Vianney on the call, Perche, who gave a talk this morning about a related topic, and Simina Branzai also will talk about similar topics. So I don't know if you guys want to say something, if you see a connection, or if you want to keep the discussion to later.